Okay, guys, today I'll discuss how to find electric field for a continuous system. Okay, I'll try to simplify it. This is a little bit difficult. So last time we have seen electric field. So the whole lecture for this session is going to be electric field. Electric field. Electric field. So electric field, I use the notation E whenever I have electric field. So, and we discussed last time, force is nothing else charge times electric field. So, and electric field is just force divided by Q. And electric field is a vector quantity and force is a vector quantity. And for a point particle, particle, electric field is nothing else. It's going to be K times Q over R squared. So that means if I have a Q, if I have a charge Q, that charge is going to create electric field everywhere. But if I ask you the electric field at point P, where P is just a space, there is nothing, and R is the distance from the charge to P. So the electric field is going to be K times Q over R squared, and K is a universal constant, 9 times 10 raised to 9 Newton meter squared Coulomb squared. So we discussed about that, and I prepared a YouTube video. Please check that YouTube video. Now today I'll discuss about if I have continuous system. Okay, so today's lecture about is continuous system. So now today's lecture gonna be electric field for continuous charge distribution. This is gonna be the electric field for a continuous charge distribution. So for example, if I have a charge like that, it can be charged either positively, okay? So I want to find electric field at point P. So this is not easy task because the charge is continuous. This an infinity number of charges are distributed uniformly on this. So if you want to find electric field at point P, it's going to be tricky, okay? Or I can have also a negative charge distribution, and I want to find electric field somewhere in space, R, where R is the distance from P to the charge Q, okay? So this is charge. So how can we find electric field if you have a continuous charge distribution, okay? For a point charge, just use this, okay? And then, as we discussed last time, you have to use also positive test charge to find the direction of electric field. But if you have continuous charge distribution, how can I find the electric field? So this is a little bit, this is calculus-based physics. You have to know how to differentiate, how to integrate, and so on. So if you have a continuous charge distribution, the electric field is nothing else. It's the integral of K dq over R squared, where dq is just a small amount of charge, okay? Infinite small amount of charge. R is the distance from the dq to the point P, where P is a point in space. There is nothing. So we want to find electric field somewhere in space at particular space. How can we find? You have to use this formula, K times dq over R squared, where K is, again, I'll repeat it, it's a constant, 10 times 10 to the power of 9 Newton meter squared over Coulomb squared, okay? Be careful. Now, the problem with that is dq, okay? Now, before even start the calculus part, you have to learn a little bit. You have to refresh your basic calculus knowledge. So first of all, if I have density, the charge density, how much is the charge density is just total charge divided by total volume, okay? Or if this is called for three-dimensional system, Q is the charge, B is the volume. But if the charge is uniformly distributed, you can fairly say that it's going to be dq over dv. So if you take the whole charge, you have to take the whole volume. If you take small charge, you have to take small volume. Since the charge is uniform, it doesn't matter. Oh, that means this is for 3D system. Okay, that means now dq is nothing else, rho times dv, where rho is charge density. This is called charge density. And this is charge, okay? This is a charge, and this is volume, okay? So this is for 3D. If you have 3D systems, you have to use this formula. And for if you have two-dimensional system, for example, if you have two-dimensional system for 2D system, so my density, let me use sigma, it's a total charge divided by total area, or I can say it's dq by dA, okay? So if you take the total charge, you have to take the total area. If you take small charge, you have to take small area. Or that means for 3D system, that means dq is nothing else, rho times dA, okay? So that's the main problem. This class is a little bit difficult because you have to know your calculus, okay? Now, if you have one-dimensional system, so now I have a charge density, the number total charge divided by the length is 1d, for example, if you have a rod, or you can say dq by dl, okay? And that means dq is nothing else lambda times dl, okay? So now we're going to use this. But the problem with that, you guys, you understand? So this is just, you have to know charge density, total charge divided by volume for 3D, dq or dv for three-dimensional system. Dq is sigma times dA, where sigma is charge density, dA is small amount of area, dq is small amount of charge, or dq lambda times dL. Lambda is the charge density, okay? Now the problem is not calculating the electric field. What the problem is, you have to know this, okay? You have to know this. Okay, now let me go to sphere. Now the problem, let me refresh your knowledge. So what's dV? dV is for what? Total volume. For sphere, it is going to be 4 pi r squared. This is dr. This is called, for sphere, it's called volume element. We call it volume element, okay? This is, dV is nothing, this 4 pi squared dr. Check it, let's check it out, okay? So if you integrate dV, you have to also integrate 4 pi r squared dr, yes? And the integral of dV is just v. 4 pi is a constant, take it out. You know, this is simple algebra, simple calculus. The integral of r squared is r cubed over 3, yes? And this is nothing else 4 over 3 pi r cubed. Oh, that's correct. This is what? The volume of what? The volume of what? Of what? Sphere, yes? So I get it correctly, thus. So whenever I ask you about to find the electric field for a sphere, for dV, you can use this, okay? Now, for a disk, okay, for a disk, dA is just 2 pi r dr. This is called for a disk or for two-dimensional system. So check it out. How could I know? If integrate dA, it's going to be 2 pi r dr, okay? The integral of dA is a, 2 pi is a constant, r dr. So if you do this, it's going to be 2 pi r squared over 2, which is pi r squared. Oh, that means I'm correct. So you can use this for a disk. You can use this for what? A sphere. Don't forget. So, and for one-dimensional system, you don't need to discuss. It's simple. Okay. Now let's use this. Okay. Now let's use this to find electric field for different systems. Okay. Now remember, how can we find electric field? Electric field is a little bit tricky concept. Yes. So this for electric field now, for a continuous charge distribution electric field, as I discussed, it's going to be K is the integral of dq over r squared. Okay. Now dq is nothing else rho dV, or dq is nothing else sigma dA, or dq is nothing else lambda dL. This is for 3D, for 2D, for 1D system. Okay. Now the problem is electric field. Okay. So use this, use this to find the electric field for a continuous system. At the same time, care must be taken here. At the same time, electric field is a vector quantity, okay? A vector quantity. means it has direction and magnitude. So to find the direction, use positive test charge. So thus, most of my students, they don't understand. They have difficulty of understanding. Some of my students can have some this misunderstanding because of this concept. So electric field is a vector quantity. To find the magnitude, the direction, the magnitude, use this formula. But to find the direction, use positive test charge. Okay? The direction of what? The direction of the positive test charge is the direction of the electric field. Okay, let me give you an example. Now, life is simple. It's not complicated. If you follow my lecture, you can understand. For example, let me have example. Find the electric field for a uniform ring, uniformly charged ring of a charge. So charge Q at point P. I'm so sorry. My electric field is like this, okay? It's like this like this. So I want to find somewhere. So my electric field is like, the space is like this. And that's the ring, total charge is Q. And then I want to find, and then this A is just the radius of the, let me give you A is the radius. And then I want to find the electric field at P. X is the distance from the center to the point P. P is nothing else, it's a space. Now the charge is uniformly charged, distributed. And if you sum all of the charge, it's going to be total Q, okay? It's going to be total Q. So how can I find the electric field for such a system, okay? So first, let's see the geometry. You have to understand the geometry. So the geometry is like, I have like this is my plane, like this is like the ring, okay? I want to find the electric field sum in the middle for the ring, okay? So first of all, if it takes infinitesimal amount of charge, dq, okay? And then to find the electric field, the direction of electric field, you have to use positive test charge. As I told you, Eloise, my dq is positive, so it's going to push my positive test charge. So my positive test charge is going to be pushed toward the cis because like charge repel each other. So the direction of the positive test charge is the direction of the electric field. And my positive test charge is going to push my positive, my dq, my positive charge, this dq going to push my positive test charge to the tortoises. But because of the symmetry, you have another dq here. Okay, dq is distributed everywhere. Oh, this dq also push my positive test charge this way. Okay, so in every direction, the electric field is in every direction. Okay, so but if you really see from Pythagoras theorem, the distance from dq to p is just nothing else, s squared plus x squared. Don't forget. Now, and then from algebra, if it's theta, this should be also theta. You know that, okay? Now, this dq, it creates electric field towards this. So you have small electric field created from dq. You have another small electric field created from here, okay? And then this dE has two components, dE cosine of theta, the x component, you learn it now. And then we have also the y component, which is dE sine of theta. So here is also, you have a dE sine of theta. So if from the symmetry, you can understand that the electric field in every direction cancels. Okay, so you have electric field, this cancels this, okay, because this is positive, this is negative, it's going to cancel out. The only electric field you have is in x direction, okay, because of in every direction going to cancel, so you have electric field only in x direction. So you have only electric field in x direction. Okay, don't forget, this is the thing. And then now let me put my equation. Now I take care of the sign. So I understand the electric field is only in x direction. So, and then A is just nothing else. The electric field is, because by definition, K dq over what? R squared. R is the distance from dq to P. How much is that? So R squared. Oh, but it's going to be K times dq. But R is the distance from dq to point P. And then if this R, and if you scale it, it's going to be S squared plus X squared. Okay? Times cosine of theta. Sorry about that. Cosine of theta. Because why cosine of theta? Because you have electric field only in x direction. So you have to take care of that. Okay? But cosine of theta from your simple mathematics is going to be adjacent, yes, over hypotenuse. So S squared plus X squared. Okay? So if you plug that value, electric field is nothing else, K times, okay, dq of S squared plus X squared. Now cosine of theta, instead of cosine of theta, plug it S squared plus X squared. So this algebra is extremely simple. So this is going to be S squared plus, so it's going to be dq x squared plus X squared to the power of 3 over 2. Okay, now guess what? A is a constant, X is a constant. It doesn't vary because it's a ring. A is always constant. A is A, always A. So you can take out X from the integral. You can take out also this from integral because X is constant, X is constant. The only variable you have is dq. But if you sum all the charges, it's going to be kxq over S squared plus X squared 3 over 2. That's it. To the power of what? 3 over 2. That's what you have to do. So it's going to be kxq, sorry for my handwriting, S squared plus X squared to the power of 3 over 2. Okay? Now, so in what direction? In positive X direction. Sorry, guys. Why? Because I have electric field only what? In positive what? X direction. Okay? So, because I already taken care of that. Now, if you want to understand for when X is much less than A, or when the ring is too big. Okay. Now you can neglect what? X. You can neglect X is much less than A. You can neglect X. Okay. So kxq, electric field is kxq. Now you compare to A is smaller than what? X. So you can neglect X. So it's going to be A squared 3 over 2 in X direction. Those algebra, it's going to be kxq over a cubed X. It's boring. It's not interesting. But the most interesting is when X is much greater than A, or if P is far. Look, if P is far means if X is extremely big, long. So if you are far away from the ring, that means before it was like that, kxq S squared plus X squared 3 over 2. Now in X direction, but now you are far means X is extremely big, so you can neglect that. Okay, you can neglect that compared to X. Physics is approximation always. Physics is a science of approximation. Always in physics we approximate. So kxq over, so this cancel this, X cubed, and then this cancel that. It's gonna be k, this X, 1k cancel 1x. So kq over X squared in X direction. Guess what? This is what? This is the electric field for what? Point particle. That's why when you see the sun, oh, the sun, look, the sun, it's like a point, but not. The sun is extremely big, but it acts like a point because it's far. So if when you are far from the chart, it's acting like a chart, like a point particle. So I recovered that. And this is the beauty of physics. Physics is really beautiful. But this is extremely simple problem because my charge is a ring, and the charge is distributed on the ring. But life will be a little bit difficult. Consider if that. What about if you have you have a disk, a uniform disk with charge density sigma, radius r, find the electric field along the central perpendicular axis of the disk. At a distance x. The same problem. I have a disk like this, okay? But this disk, the charge is uniformly distributed. So a little bit difficult problem, okay? And then the charge is distributed. I want to find electric field. This is the center at P, okay? And then I want to find the center. This is x. X is constant always. But my problem is now the small r. This is r. R is variable now because my charge is distributed everywhere. That's the problem. It's gonna give me a headache. So, and the charge is distributed everywhere. Okay. So for instance, now it just take one ring like that. So if you add all the ring, it's gonna be the disk. You understand me? So if you have dq here, dq, and you need positive test charge. So this dq gonna push my positive test charge towards this. But I have another dq here, gonna push my positive test charge that direction. So this is my electric field as before, okay? And this is theta, and then this is theta, okay? Now the problem is, okay? Because as I told you, the charge is distributed and the symmetry, okay? From the symmetry, if you have some dq, and then to find the direction of the electric field created by the dq, you have this positive test charge. Because my dq is positive, it's going to push my positive charge down. But from the symmetry, you have exactly another dq in a positive direction. That's going to push also your positive charge like that. So in other words, this dE, you have one dE from here, you have another dE from here. And this is theta, okay? And this is dE cosine of theta. And you have dE sine of theta up, and then you have dE sine of theta down. So like before, because of the symmetry, okay? Because of the symmetry, every electric field in other direction cancel, except at the electric field in x direction. So the electric field is, now one second, the electric field is in only x direction, okay? So it's only on x direction. You have only electric field only in a x direction. So we're gonna take care of that. But this problem is a little bit difficult again, because why? Now this is r, this is x. Guys, let me clean this. So it's a little bit boring. Okay, don't forget. This is x. So, and this is what? X squared plus r squared. X. But this x is constant, but my r is, remember, my r gonna be what? It's continuous. It's gonna increase until what? you go to R, capital R. So this R, small r is variable. X is constant. That makes your problems extremely difficult. So this R is variable. So you can go, it can be here, it can be here, it can be here, it can be here, or it can be here, it can be here. So it's everywhere. So it's a variable, but X is only constant. So this integral will be a little bit difficult. Don't worry, it's simple. So the electric field from our definition is going to be dq over what? dq over r squared, dq over r squared. But we have electric field what? Only what? In x direction. So you have to use cosine of theta. And then, but k dq, okay? R is the distance from dq to point P. So that is this. Oh, I'm so sorry. I don't want to use R actually. So I don't want to use R. So dq over r, dq over what? The distance from here to here squared. This is x squared plus r squared. Okay. Now, and this cosine of theta. Why cosine of theta? Because the electric field is only in x direction. So you have to take care of that. So this is the integral of x squared plus r squared and times cosine of theta. But cosine of theta is adjacent. Cosine of theta is adjacent over hypotenuse. So you have to take care of it, adjacent. So it's going to be, so this is cosine of theta. This is going to take care of the direction of the electric field. You have electric field only in x direction. So it's going to be k. Now, x is a constant. You can take it out if you like, okay? You can put it or it can put it out because x doesn't vary because x is a distance from here to here. So, and then from your simple algebra, it's going to be x squared plus r squared or 3 over 2 times x, okay? Now, in principle, you are done. But life's not simple like that, okay? It's not simple because this integral is difficult. So what kind of system is that? This is what? A disk, yes? And for a disk, I discussed already, dq is 2 pi r dr. I discussed already in the beginning of the lecture, dq is 2 pi r dr, okay? So it's going to be k, instead of dq, we can have 2 pi r dr x over x squared plus r squared. Don't forget 3 over 2 to the power of 3 over 2. Now, this is my integral. So it's a matter of integrating. So how can I integrate? So basically, you are done. So basically, you are done. So the electric field is only in x direction. Don't forget, the electric field is only in x direction. The electric field is only in x direction. Okay? The electric field is only in x direction. Okay? This x hat is nothing else but the direction of the electric field. Now, it's a matter of simple calculation. So now when I calculate this from your simple calculus courses, so this I have to integrate it, but I have to have a trick. So let me r squared plus x squared is m. So dm is nothing else to r dr because x is a constant, doesn't worry. Okay. Now what you have to do is just plug that value. Okay. Now this is gonna be 2r is nothing else. Okay. 2r is nothing else. Okay. 2r is nothing else. Yes. So 2r is just dm. 2r, dr is 2m. Okay. Put pi is there, x is there. Don't worry. Okay. And because you look at 2r, dr is just this. Just plug that part, but p and x is remaining there. X squared plus r squared is just m to the power of 3 over 2. Now, when you do this integral, let me finish x, pi x is, you can take it out. The integral of dm, m3 to the power of 3, 2. And then, you know, from your, when you integrate that, simply going to be what? Minus 3 over 2 plus 1. Okay? So do that. If you do that, you'll get, it's going to be m minus half over minus half. Yes? So it's going to be k pi x. A pi x. Where is decrease 2 pi r sigma there is a typo error. Yes. So be careful. DQ is nothing else. DQ is sigma is missing. 2 pi r dr sigma. So there should be sigma here. Okay, there should be sigma here. There should be sigma here. So 2 pi x sigma is common, 2 pi x sigma. The integral of that is already this one is already, I take care of it, m minus half, m minus half, okay. Let me make it clear. M minus half, okay, minus half, okay. So this, nothing else. Look, those algebra is going to be minus 2 pi x sigma, because this is going to go up over square root of m in x direction. My electric field is in x direction. My electric field is in x direction, in x direction, in x direction, okay? And yes, this is just, okay, minus 2 pi x sigma over square root of m, because in x direction, now plug the value again, minus 2 pi x sigma, okay, still I'm doing the algebra. So square root of m is nothing else. M is just x squared plus r squared. And x, r varies. Only variables are because the charge is distributed. R varies. This is an x direction. R varies from 0 to r. Okay. So if you do this algebra, it's going to be 2. Now you can plug this r here. You can plug this r here. So it's going to be 2 pi. So if you plug x, this x squared cancel x, it's going to be 2 pi k sigma minus 2 pi x. Now, when you plug this r, it's going to be 2 pi x sigma over square root of x squared plus r squared in x direction. Okay. Okay. Now, this is how you find electric field. So first I do the substitution technique. Then after that, I arrived here, and then I plug back the value of m, and then I get that. And then I do the integral. This is the integral 2 pi x sigma over x squared. Now, if you take when r is extremely bigger than x, means when big what disk. Okay, when you have a big disk, oh, you can neglect r. Yes, you can neglect r. So and this is when r is extremely big, this is going to be 0. So it's going to be p k sigma, because 1 over big number is 0. Okay, so you have only this term, and then 2 pi, but k is 1 over 4 pi epsilon, that we learned it before, times sigma, and then this is going to be sigma over 2 epsilon in x direction. So that if you have a disk, big disk, okay, finally the electric field, okay, the electric field doesn't depend what? The electric field doesn't depend, okay, on the radius or distance, something like it depends only on charge density and epsilon. Epsilon is 8.85 times 10 to the power of minus 12. 1 over 4 pi epsilon is just k. So I found, so this is how you find electric field for a continuous system. I hope if you have any difficulty, please ask me in a comment section. Okay, thank you very much for your understanding. Whenever you have any question, I'm here to help you guys.